Hi everyone, this is KDTrees, and we're going to discuss briefly about the fact that how KDTrees actually are just a slightly different implementation of binary search trees, which most of us are really familiar with. This allows us to have the basic understanding that every node has data stored in it, and then every subsequent child node has either a node to its right or its left. The only difference between a KD tree and a binary search tree is the KD tree's exceptional ability to divide the data into more than just two dimensions, allowing us a lot more granularity in understanding the data that we have stored in the data structure. Ideally, this is used for nearest neighbor, which is an algorithm used to understand the similarity between multiple data points based on how close they are in different dimensions. And it works really well for us because that's exactly what our application works on. Our main focus was information retrieval. But before we discuss any of that, I'd like to delve deeper into how a KD tree works. As you can see here, a KD tree is basically a binary search tree that divides the data into separate compartments based on any user-defined criteria. While for here, to ensure simplicity, we've only used two-dimensional data. Our application actually uses 784 dimensions at its lowest and up to 1,000 dimensions at its maximum. This allows us to have an even wider array of an opportunity to understand the similarity of data from more than just a very limited perspective. So as you can see with the definition here, it is just a binary search tree where data in each node is a k-dimensional point in space, which means that we can have k levels of dimensions at every depth of the tree itself. So in short, it's a space partitioning data structure for organizing points in a k-dimensional space. This allows us to actually divide the data in as many partitions as we want to ensure an even granular level of access and to ensure that our nearest neighbor algorithm works even more accurately. For this example, we've used two-dimensional data because it's easy to visualize, but you can imagine the implications of this in hundreds and even thousands of dimensions. So for here, we basically started off by using KDTrees in search engines for text. And while that worked wonders, KDTrees were exceptionally well in using their nearest neighbor algorithms to find similarities between different images. So you might have noticed that Google has this feature of searching for visually similar images. And that is actually a functionality that we can easily implement through KDTrees, because they can store every individual pixel at a different dimension and then use all of them to compare to different images of that many or even more dimensions, allowing us to understand which images are visually similar to each other. And then once we implemented both of them, both the search engine and the image similarity algorithm, we were really excited to find out that KD trees are actually far cooler than what we first anticipated of them. And while we'll go deeper into how we implemented our application, this is just an overview of the techniques and methods. We developed a web template using the Django framework, and then also implemented both abstract preprocessing through the vectorization of the data using the scikit library. And then we put that data into the nearest neighbor algorithm that we implemented. And we're really excited for showing you the results very shortly. I hope this was informational for you guys, and I hope you enjoyed our presentation. Thank you so much for watching, and best of luck to everyone else presenting as well. That's all from us. Goodbye.